A robot peels an apple. 2 hands, 10 fingers, working together. One holds, the other controls a blade, adjusting grip as the fruit rotates. This is what separates a humanoid that does useful work from one that just walks around a stage. Right now, 5 different approaches to robot hands are competing, and they disagree on almost everything. How many joints, what kind of sensors, where to put the motors, and how much complexity a factory can actually build. This is where the humanoid race gets decided. Start with the basics. A degree of freedom is one independent way a joint can move. Bend your index finger. That is 1 degree of freedom. Now spread it sideways. That is a second. Your entire hand has roughly 27 degrees of freedom, controlled by muscles in your palm and your forearm, connected by tendons that thread through your wrist. More degrees of freedom means more kinds of motion. But every extra joint needs a motor or cable, a sensor, a control signal, and another part that can fail. That trade-off between capability and complexity is the central fight in robot hands right now. Tesla's approach starts with a patent. Published internationally in April 2026, it describes what Tesla calls a mechanically actuated robotic hand. The key idea: move the motors out of the hand and into the forearm. The patent shows actuators packed into the forearm housing, connected to each finger by 3 flexible control cables that route through a wrist transition zone. Each finger gets 4 degrees of freedom. The cables run through channels designed to reduce friction and keep one finger's motion from interfering with another. This follows the same basic strategy as the human hand. Your finger muscles are not in your fingers. They are in your forearm. That keeps your fingers light and nimble, while the heavier, powerful parts sit farther back. Tesla's patent copies that principle with engineering materials: cables instead of tendons, electric motors instead of muscle. The timing is significant. According to earnings call reporting, Tesla is aiming to start Optimus production around late July or August 2026. That means this patent describes a hand architecture Tesla wants to manufacture at scale, not just demonstrate. Then there is Sharpa Wave. In June 2026, NVIDIA announced its Isaac GR000 reference humanoid robot, a Unitree H2 Plus chassis, an NVIDIA Jetson Thor processor, and 2 Sharpa Wave hands. 22 degrees of freedom per hand, 75 total across the whole robot. Sharpa built the Wave at 1:1 human scale. Each fingertip carries what they call a dynamic tactile array, a dense grid of pressure sensors that lets the hand feel shape, texture, and slip. Fingertip force exceeds 20 newtons, roughly the grip strength needed to twist open a bottle cap. And Sharpa has the demos to back it up. 2 Wave hands peel an apple without crushing it, install a graphics card into a motherboard, position screws, and plug in power connectors. These are tasks that require coordinated finger motion, pressure feedback, and real-time adjustment. Figure takes a different path. Its 3rd-generation humanoid, Figure 03, does not publicly advertise a high degree of freedom count. Instead, Figure focused on what the fingers can feel. Each hand has a palm camera for close-range vision and custom tactile sensors on every fingertip that detect forces as small as 3 grams, roughly the weight of a paperclip resting on your finger. The fingertips are compliant, meaning they give slightly under pressure instead of staying rigid. That helps them conform to irregular shapes and detect whether a grip is slipping before the object falls. Figure also redesigned the hand for mass manufacturing, reducing part count and using high-volume production processes. For a look at what happens when cost is not the constraint, there is Shadow Robot. The Sharpa Dexterous hand has 20 actuated degrees of freedom, 24 joints, 20 motors, tendon drive, and over 100 sensors running at up to 1,000 readings per second. It weighs about 4 kilograms and is used in research labs, not factories. Shadow shows what full dexterity looks like when you can spend the engineering budget, but it also shows the cost. Hundreds of parts, dense wiring, specialized tendon routing, and a price point that rules out mass deployment. It is the reference standard, not the production target. And then there is the argument against all of this. Agility Robotics builds Digit, a humanoid designed for warehouse work. Digit does not have a 5-finger hand. It uses interchangeable end effectors, simple grippers that snap on and off depending on the task. Move totes, attach the tote gripper. Handle packages, switch tools. The logic is straightforward. If the job is repetitive, a proven single-purpose tool is more reliable and cheaper than a general-purpose hand. Boston Dynamics makes the same point with Stretch, a warehouse robot that unloads trucks using suction grippers. No fingers at all. It handles thousands of boxes per shift. For structured environments with known objects, the simple tool wins. So where does this leave the scoreboard? Tesla is patenting a tendon-driven, forearm-actuated hand designed for production scale. Sharpa Wave has 22 degrees of freedom with dense tactile sensing and is now the reference hand for NVIDIA's humanoid platform. Figure 03 prioritizes touch sensitivity and manufacturability over raw joint count. Shadow proves what full dexterity costs, and simple grippers prove that many real jobs do not need dexterity at all. There is one more possibility worth considering. Robot hands do not have to copy human anatomy. A finger that rotates freely around its own axis could turn a screw without repositioning. Extra fingers could stabilize objects that human hands fumble. Tactile sensors that cover the entire palm and every joint surface, not just the fingertips, could detect contact that humans cannot feel. Stronger materials could grip harder without fatigue. None of that is production-ready today. The bottleneck is still reliable control software and manufacturable hardware. But the direction is clear. Robot hands are getting more capable, cheaper to build, and closer to doing real work. The company that ships a hand dexterous enough to handle unexpected objects, tough enough to survive a factory shift, and cheap enough to put on thousands of robots is the one that wins the humanoid race.